Video 64 of the master course, Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is configuration interaction. In the last lecture, we talked about the multi-configurational STF wave function and method, where we have a wave function which is a linear combination of different determinants or configuration state functions. And we simultaneously optimize the expansion coefficients in this linear combination and the molecular orbital coefficients. The configuration interaction wave function is also a linear combination of Slater determinants, but here we do not optimize the molecular orbital coefficients. So one generates a set of determinants by using a fixed and unchanged set of molecular orbitals. Typically, one starts with a Hartree-Fock calculation, optimizes the orbitals in a Hartree-Fock calculation, and then generates a set of Slater determinants and maybe combines them, spin adapts them to get configuration state functions, and uses these determinants or configuration state functions as the basis for our configuration interaction wave function. So in this configuration interaction wave function, the orbitals are fixed. And therefore also means that when we optimize the energy, because configuration interaction is also a variation method, then we only take the derivative of the energy with respect to this determinant or configuration state function coefficients and set it equal to 0. Normally, one writes the configuration interaction wave function out in terms of the Hartree-Fock wave function and contribution from all the excited determinants. Where then what one has to do in this method is to find the values of these expansion coefficients here. So the wave function here is just a linear combination, which means if we then do the variational calculus, it's really a proper linear variational calculation, and we end up with a set of linear equations, which we can conveniently write as this matrix equation here, and rewrite it then as this matrix eigenvalue problem, where ECI is our configuration interaction energy, C are a column vector of the expansion coefficients in our wave function, and H is the Hamiltonian matrix, so it's the configuration interaction or CI matrix, which contains the matrix elements in this matrix are integrals over the unperturbed molecular Hamiltonian and all the determinants. So it will be the Hartree-Fock determinant and all the excited determinants. Finding the expansion coefficients then in this CI method involves that one has to calculate all the elements of this CI matrix, meaning all the integrals over the Hamiltonian with the different Slater determinants, build the matrix in principle, and then diagonalizes. In practice, there are different algorithms used which never require to have the full matrix available at the same time, but in principle, it's just diagonalization of this matrix. When one then evaluates these integrals over the Hamiltonian and the different Slater determinants, a set of rules, which are called the Slater-Condon rules, become that very useful. These Slater-Condon rules are actually not rules in the context of requirements, but they are a collection of the results one obtains when one takes integrals over Slater determinants. And there can be different kinds of integrals. One of them could be overlap integrals between different Slater determinants. And the other set of integrals will be integrals with some operator. That could be a sum of 1 electron operators, it could be a sum of 2 electron operators, or it could be just our unperturbed molecular electronic Hamiltonian. And I will illustrate or will give you the results for 2 of these kind of integrals with the molecular Hamiltonian. And what the rules are all about is then one looks at how do the 2 determinants, the determinant in the bra and the determinant in the cat, in this integral differ by each other. And differ means by how many of the spin orbitals or spatial orbitals do these determinants differ. And one then distinguishes by different cases if they do not differ, if they differ by one spin orbital, if they differ by two spin orbital, or if they differ by more than two spin orbitals. Now, if the two Slater determinants are the same and takes the matrix element of the Hamiltonian, then we get an expression similar to the Hartree-Fock energy, just with the kind of orbitals which were included in these two determinants. Now, if they differ by one spin orbital, so in the ket here, we have replaced the spin orbital p, which was in the bra, by another spin orbital r. So there's difference in one. And the result of this matrix element then is just the integral with these two spin orbitals, which sort of were replaced with the core Hamiltonian, and then a sum over all the other spin orbitals which are included in both the determinants in the bra and the determinant in the ket of these of the Coulomb and exchange integrals, where we have p and r, and then a sum here over the remaining spin orbitals s. Now, if the difference is two spin orbitals, so the two spin orbitals p and q, which are included in the determinant in the bra, are in the ket replaced by the spin orbitals r and s, then we actually get just two integrals, two electron integrals. We get one Coulomb and one exchange integral, given by actually these four spin orbitals p, q, r, and s. And if the difference is more than two spin orbitals, then the integral is zero. The last result is actually very, very useful because it means that from this large configuration interaction matrix H, all the parts where the two Slater determinants differ by more than two spin orbitals, we know that the result is zero. We don't actually need to evaluate this matrix element explicitly. We only have to look at how large is the difference in terms of spin orbitals between the two Slater determinants, and if it's larger than two, we know it's zero. And for the one where it's not larger than two, we have these rather simple expressions here and here. Now, there's another useful result which we can use when we want to evaluate all the elements of this CI matrix, and that is if we have the particular matrix or the particular integral where we have the Hartree-Fock determinant and a single excited determinant. Then these integrals where we have the different single excited determinants, they are all zero, because if one evaluates this, it turns out that this is actually an integral over the Fock operator with the occupied orbital I, this one, and the virtual orbital A, this one. Now, if the spin orbitals are the solution to the Hartree-Fock equations, then these kind of integrals over the Fock operator, where we have occupied and virtual spin orbitals, they are all zero, because one solves the Hartree-Fock equations by diagonalizing the Fock matrix in the basis of the orbitals, and which means that this integral, which belongs to the off-diagonal block, is zero. And this result is called the Brunner theorem, which is of course very useful because there's another set of integrals over the Hamiltonian which is zero.